So, dear friends, I hope everybody is fine. I hope all the students are fine. And in this video, we'll be talking about hydrogen atom and uh, and uh, and this problem of hydrogen atom. In this case, we would like to write down this Schrodinger's wave equation for hydrogen atom. And as we know, we have talked about hydrogen atom in principle, where we have used the postulates of Bohr's model and and uh, and could calculate out the quantization of energy in case of hydrogen atom. Now, I think that this was the first problem that was tackled by Schrodinger with his new wave equation that he used it for hydrogen atom, and even though the mathematics that is involved that's heavy. But finally, the reward was given to Schrodinger for explaining the naturally quantizations that occur when Schrodinger's equation is solved, and it's certainly valued for Schrodinger. And and if we have to start with what we should say is that in a hydrogen atom, what we have is we have one proton, and and we have an electron, and this electron is outside the nucleus, and it has a charge, and and it has the mass. Now, for the sake of convenience, I mean, we would like to consider that the proton is at at stationary, and and electron is moving in vicinity. But the motion of this electron that we have, this motion is prevented, so that the electron does not escape this nucleus. And if we rightly go back to the Bohr's theory, the correction for proton motion, it was simply a matter of replacing the electron mass by the reduced mass of the system. Now, what should we start with here is that let's write down the Schrodinger wave equation for hydrogen atom, and let's write it down in terms of Cartesian coordinates. So if we write it down, it is dou 2 psi by dou x2 plus dou 2 psi by dou y2 plus dou 2 psi by dou z2. Then what we have is 2m by h cross squared, then E minus V of psi, and this thing is equal to 0. Now, this is Schrodinger's wave equation in Cartesian coordinates. And, and this E is the total energy. It's the total energy. It's the total energy of electron. And this V is the potential energy. Now, these are the two important parameters. And if we have to write down this V, this V is negative, and we have E squared by 4 pi epsilon naught, and then we have R. So this potential energy term that's appearing in Schrodinger's wave equation, it has a correlation with the R. It's directly dependent on R. And since this potential energy is the function of r rather than that of x, y, and z, we cannot substitute this equation into the equation that we have here. And certainly there are two alternatives. There can be two paths. One is either we should express this potential energy in terms of the Cartesian coordinates, or or it should be replaced by the Cartesian coordinates in terms of writing down it in terms of x, y, and z. The other path can be to express this Schrodinger equation that we have in terms of spherical polar coordinates. And when I say spherical polar coordinates, then I'm immediately talking about r, theta, and phi. So certainly, if we go into the symmetry of the problem and the physical situations, going into the spherical polar coordinates seems to be plausible. And the spherical polar coordinates that we have in terms of r, theta, and phi. And we call this 2. Okay, it's taking light. Okay. So what we have is we have r, radius, theta, and phi. Now these are the three things. Now this r is what it refers to the length of the vector. So in order to have a mere speculation or an idea about it, if I draw something like this, where I have a position vector r. Now this is a three-dimensional geometry, and we have, say, point P in the space. Right? And if we have to measure this r, we can measure it as under root of x square plus y square plus z square. So this is x coordinate, and no, I have to start from here. This is x, and if I choose this as y and this as z. So what am I trying to tell here is that we have theta now. This theta is the angle that's lying between the z coordinate and the position vector p. And this theta is also called as zenith angle. It's also called as zenith angle. And this theta can be calculated, and we can write down cos theta for it, and cos theta will give us z by under root of x square plus y square plus z square, z by r. That should be the case. So this zenith angle, this theta, can be written as cos inverse of z by r. So we have theta and we have r, and I have written down this at the wrong place. No problem. Let's proceed from here and see. And then what we have is the azimuthal angle, what is called as phi. And if we draw a perpendicular from here on the plane of x and y, and we will have this whole plane that will go like this. Okay, and this angle that this plane makes with x is called as phi, and this phi is called as mutual angle. And we can have the transformation equations for for transforming the coordinates into r, theta, and phi, and the equations that we have for x, we can have simply r sine theta and cos phi, and for y we will have r sine theta sine phi, and for z we'll be able to calculate is r cos theta. These are the set of equations that we can achieve from using right angled triangles and obtaining a transformation equation from Cartesian coordinates to the polar coordinates. Now, when we do the transformations and we look for all the derivatives that are involved, we come up with Schrodinger's equation in spherical polar coordinates. So what we come up with is Schrodinger equation in spherical polar coordinates. And on. So writing down this Schrodinger's wave equation in terms of spherical polar coordinates r, theta, and phi, what we obtain is 1 by r square dou by dou r of r square dou psi by dou r, plus what we have 1 by r square sine theta, then dou by dou theta times sine theta dou psi by dou theta, plus 1 by r square sine square theta dou 2 psi by dou phi 2, plus 2m by h cross square e minus v, which is defined already, psi is equal to 0. So this is our Schrodinger's equation in spherical polar coordinates. By making use of these transformation equations, x equal to r sine theta sine phi, y equal to r sine theta sine phi, and z equal to r cos theta. Here, of course, it is cos theta. Many a times I have told you I have the bad handwriting, but you have to bear with me in terms of the handwriting that I have. So this is Schrodinger's wave equation in polar coordinates, and this in this equation we should be able to substitute the value for v, which is purely in terms of the radius vector r, and when we do that, we will have the equation that we are interested in. And what we do in this equation is we multiply this whole equation by r square sine square theta, and what we do is we use the expression for v, which is minus e by 4 pi epsilon naught r, and what we get out of this is we have sine square theta, okay, because r square and r square will cancel and you'll be left with sine square theta dou by dou r times r square dou psi by dou r. Okay, then we have 1 by r square sine theta, so here we will be left with sine theta dou by dou theta of sine theta, then we will have dou psi by dou theta. All right, that should be the case, and then plus this thing will go, r square sine square theta will go with r square sine square theta. What we'll be left with is dou 2 psi by dou phi 2 alone, then we will have 2m. All we have to do is to multiply this with 2m r square sine square theta divide by h cross square. And inside, so the bracket I would like to give here, we will have for E, we will have E, and then for V it will become plus E by 4 pi epsilon naught r, and close this thing and multiply this thing with psi, and this thing is equal to 0. So we have an equation here, and certainly this equation is the partial differential equation for the wave function psi, for psi, for wave function psi. That should be clear. For an electron which is in a hydrogen atom. Now, together with various conditions, what is important here is that this psi that we have, this psi must it must obey that this psi should be it should be normalizable. And we understand what's the condition of normalization, and that this psi that we are talking about, this psi and its derivative should be constant and should be single valued at each point for r that we have, for theta that we have, and for phi. Now, certainly, this equation completely specifies the behavior of the electron. It completely specifies the behavior, and to exactly observe the behavior, we have to go in actual mathematical transformation. And we will not go through that rigorous mathematical operation. We would try to understand what is important to understand from solving Schrodinger's wave equation on hydrogen atom. So this equation can exactly be solved, and it turns out, on solving this equation, what we find is we find 3 quantum numbers. So on solving this equation, what we find is we find three quantum numbers. What we find 3 quantum numbers. And we are in a position to understand that in place of single quantum number, the single one that we have, single quantum number, where we have the single quantum number, it is in Bohr's theory. And that single quantum number is n. When we solve for hydrogen atom, we come up with a single quantum number, and that is n, what we call as principal quantum number. And this single quantum number that we have from Bohr's theory, and what we if we go back to the Bohr's model, the electron's motion is basically one-dimensional. The electron is moving in just one dimension. It's moving in just one dimension. Since the only quantity that varies as it moves is its position. So what varies is the position of this electron around the nucleus. And that's why we call this as one-dimensional motion. And one quantum number that we have in Bohr's theory, this one quantum number is enough. It is enough to specify the state of such an electron. And just as one quantum number is sufficient to specify the state of the particle in one-dimensional box. If we go back to the problem of particle in box, and here we are able to find quantization in terms of this n, and this n can specify the energy of the particle in one-dimensional box. So there you need only one set of quantum number. Now, a particle in three-dimensional box, which we have already discussed in terms of Cartesian coordinates, it certainly needs three quantum numbers for its description. Why? Because now there are three sets of boundary conditions for the particle. You have the wall along x, you have the wall along y, and you have the wall along z. And what is important there, if you rightly remember, is that psi must be zero at that wall. If this is a wall, here psi has to be zero at wall of the box. So you have independent zeros. You have along x, you have to have psi equal to zero. Along y, you have to have psi equal to zero. And if we go into the problem of hydrogen atom, the electron's motion is basically restricted by the electric field of the nucleus. The electron's motion is restricted by electric field of nucleus. And instead of the walls that we have in case of the particle in a one-dimensional box or particle in a two-dimensional box, what we have here is the potential, this potential that due to the electric field. This potential is there, and this electron is free to move in three dimensions, and it is accordingly not it's not surprising that three quantum numbers govern the wave function as well in case of this hydrogen atom. And we have the conventional way of doing it. What we do is we make use of the mathematical technique known as separation of variables. And in that case, what we do, we start with the wave function psi, which is the function of r, theta, and phi, and make it dependent on r of r, theta of theta, and phi of phi. And we have discussed this kind of problem also in terms of Cartesian coordinates when we were discussing particle in a box, in three-dimensional box, where instead of r, theta, and phi, we had x, y, and z, and z. So what is the advantage of writing this Schrodinger equation in spherical polar coordinates for the problem of hydrogen atom? It is basically that in this form, it may be separated. It may be separated into the three independent equations. The equation in terms of r, another equation in terms of theta, and another equation in terms of phi. So this separation is plausible, and we automatically come across some constants by virtue of which these equations are to be satisfied. And if I choose this as the solution of Schrodinger's wave equation that we have already written over here, the Schrodinger's wave equation in spherical polar coordinates. So all I have to do is to differentiate this equation in terms of r, in terms of theta, and in terms of phi. And when I differentiate it with respect to r, the other two parameters will not be the function of the differentiation. They will behave as constants. So what we are going to achieve after this, is what I'll be doing is I'll be taking this psi as r theta and phi, and taking the double derivatives and the double derivatives, the single derivatives, whatever. So suppose I take dou psi by dou r. So what I'll get here is this theta and phi will be outside, and I will have dou r by dou r. And similarly for dou psi by dou theta, this is capital theta, this is small theta. Okay, for that it will be r will be constant, phi will be constant, and what I will have the capital theta with respect to the small theta. And we can have the double derivative, say dou 2 psi by dou phi 2, and that will be r theta dou to the big phi divided by the double small phi. So this set of equations, what we have is we have to use this set of equations in what's called as Schrodinger's equation in spherical polar coordinates. And when we do that, we come up with this equation. We come up with this equation where we have things in terms of theta, in terms of r, and in terms of phi. Where is that? Okay, so here I have the r part, I have this part, and I have 2mr square sine square theta h cross square. Okay, for that what we will have is we will have for phi part, I have missed that here, that is 1 by phi d2 capital phi by d small phi 2. So when we make this set of substitutions, in the Schrodinger's wave equation, which is in spherical polar coordinates, we are able to obtain this equation. So this is our equation where we have got rid of psi. There is no psi right now. The psi is now in the form of r's, thetas, and phi's, of whose probability densities will matter in some later stage. Now the point is that what we have here is the Schrodinger's wave equation, and we have r acting as an independent quantity, theta acting as an independent quantity, and so many things. Now, if I do transfer this part of this equation to the right hand side, what am I going to get? I'm going to get here is I have to write down the same thing, d by dr of r square dr by dr plus sine theta by theta d by d theta of sine theta. Then we have d capital theta, d small theta, and then we will have plus 2mr square by h cross square, then sine square theta times e square by 4 pi epsilon naught r plus e. This is equal to 1 by phi d2 capital phi by d phi 2, the small phi that we have. Now this equation that we have in terms of r, theta, and phi, and of course we have energy term here. This equation can be correct only if we have to make some sense out of this equation. If both the sides of this equation are equal to some constant, and that constant should be same, that the constant that we can use for the left hand side, the same constant I should use for the right hand side. And since they are functions of different variables, here, we'll be able to see that it is convenient here. It is simple to call this constant for the sake of mathematical subjectivity. It is fine to call this constant as ml square. And in doing so, what's going to happen in this equation is that this should be minus times, because we have transformed it from one side to another side. So this minus 1 by phi d2 phi by d phi 2 must be equal to ml square. This should be the one way of talking about it. And this whole thing should also be equal to ml square. And when we will do that, let me call this, say, for example, a for the time being. And what is the other part of the story is that this whole thing on the left hand side, this whole thing is equal to ml square. And we will do that. And what we will do is we will write down the equation for that. So what would it look like is we can have, what we can do here is, I would like to multiply this equation that I will have here. I would like to multiply, because this whole thing is equal to ml square. I would like to multiply, I would like to, what am I saying here is, I would like to divide this whole equation in terms of ml square by sine square theta. And what will so not multiplying, I have to divide. So dividing by sine square theta. So when I do that with this part, what am I going to get is 1 by r d by dr of r square. Then what I will have is dr by dr. Okay, that should be the case. And bring it close, plus 2mr square by h cross square, because this sine square theta will die with the sine square theta with whom I have divided it, times what I'll get, e square by 4 pi epsilon naught r plus e. Okay, that should be the case. And I would like to transform this thing to the right hand side, but what is in the right hand side at the first moment? It is ml square, and I have divided the whole equation by sine square theta. So here I will have ml square by sine square theta. That should be the case. And this term I will shift on the other side. This will give me minus sine, this will be 1 by, because I am dividing this by sine square theta. This will give me 1 by theta sine theta. Okay, then d by d theta sine theta, and d theta by d theta. And that should be the case. Very crazy. And so what we have introduced a constant ml square, and we are able to separate out a propellant from the rocket. We have a rocket equation, and we are separating out this propellant from this rocket, and we have a separate equation here. Now, going on the similar lines, if we again have an equation in which we have different variables, you can see they are appearing on the both sides of this this equation, and we require that both the sides of this equation should be equal to same constant, and this constant is chosen as this constant that we will use here is chosen as L times L plus 1. And it has more than one reasons to choose this constant equal to L into L plus 1. And this is another important reason in itself over ml square, what we have chosen in the previous case to have it L into L plus 1. And the equations for theta and r can be separated out. And I would like to write down those equations. One I would like to write down. So this is the constant introduced here. This is the constant introduced. And if there is a question why, the answer to this thing is because it works. There cannot be any other answer other than that of that I'm trying to give here. So what we will have an equation ml square by sine square theta minus 1 by sine square theta. Okay, so it's not sine square, it is theta sine theta. So theta sine theta d by d theta of sine theta, and then what we have d theta by d theta, and this thing is equal to L into L plus 1. Okay, and for the radial part that we have now, what we will have is 1 by r, then we have d by dr, then we have r square, then we have dr by dr. Okay, that's fine. Then plus 2m r square by h cross square. Then we have e square by 4 pi epsilon naught r plus e, and this thing is equal to L into L plus 1. Now these equations that we have, the equation that we have here in terms of A, I may call this B and I may call this C. So this equation is exclusively in terms of phi, and then we have another equation in terms of theta, and then we have another equation in terms of r. Now to make them pure differential equations in terms of theta and phi, once you make the rearrangement of these right hand sides that we have ml square L into L plus 1, when you do that you will come up with three independent equations. So you will have what you will have is the very first thing you will have is the equation for phi. That's clear from the equation that we have got. What is that? That is d2 phi by d phi 2 plus ml square phi is equal to 0. This is your equation for phi. And see the power of separation of variables. Okay, the next important equation that you will come with is equation for theta. So equation for theta. So what will be that? That will be 1 by sine theta d by d theta sine theta d theta by d theta. Okay, that should be the case. And what would I like to do is to transform this L into L plus 1 to the left hand side and put it in some bracket. So in transforming the numbers, I'll get L into L plus 1, then minus ml square by sine square theta. This whole thing is with theta is equal to 0. So you have another equation for we have a separate equation for theta. And then the third important equation that we have is equation for r. So equation for r. So for that what we will have is we have 1 by r square, okay, d by dr times r square dr by dr times plus, if I start with some bracket, 2m by h cross square times E square by 4 pi epsilon naught R, then plus E. Okay, then close it, and then we have minus L into L plus 1, bracket close, divide by R square, bracket close, in terms of capital R is equal to 0. So this is the set of three equations we obtained using variable separable approach. In our next videos, I would like to have some discussion on these equations that come up on using the approach of variable separables for hydrogen atom, and using Schrodinger's wave equation in spherical polar coordinates, and transforming this equation in terms of r, theta, and phi, making them as function of psi, getting rid of psi, and finally using variable separable approach to come up with these three independent equations: equation for phi, equation for theta, equation for r. That should be the case. If I have committed any mistakes in what I have tried, I apologize for that. And guys, let's meet in some other video where we would like to have a discussion on spontaneously coming up of quantum numbers, the three quantum numbers we'll be discussing. Okay, goodbye.